The recording has started. Okay, hi everyone. Welcome to this week's talk. This week we're going to talk about enhancing perfSONAR and measurement capabilities for T4 switches. Feel free to take it over. Thanks.
Hello, everyone. Thank you for joining. So as the host said, I'll be presenting the work enhancing perfSONAR measurement capabilities using P4 programmable switches and adaptive sampling. So for our presentation today, I will start first by the motivation for the need of ScienceDMZ. Then I will give a brief background on ScienceDMZ, perfSONAR, P4, and linear prediction. Moving forward, I'll be discussing the proposed system, the experimental setup, the corresponding results. And before concluding this presentation, I'll describe a library we are working on that shows how to combine perfSONAR and P4, and then we'll conclude this presentation. So why do we need ScienceDMZ? First of all, ScienceDMZ is a network designed for big science data transfer. It's designed to support high throughput, high latency application. So what do we mean by high throughput, high latency applications, and why do we need such a design? And the answer is in this graph here. So to have reliable data transfer over the network or the internet, typically use TCP. And TCP has different congestion control algorithm to avoid congestion, of course, and to operate based on the packet losses. So every time a flow or a data transfer has a packet loss, it reduces its throughput. So this becomes more severe as the round trip time increases. So in this graph on the y-axis, we have the throughput in gigabits per second. On the x-axis, we have the RTT, round trip time in milliseconds, and we are depicting the relationship between the throughput and the RTT for some of the congestion control algorithms. So the purple line shows the throughput when there's no packet losses. And the other three lines shows, the red line, for example, shows the measured throughput for TCP, HTTP congestion control algorithm, the blue one for the Reno congestion control algorithm, and the dashed green line, this one, for the theoretical TCP Reno throughput. And here we are having 0.0046 packet loss, which is relatively low. But as you can see, if the RTT is larger than 10, or as the RTT increases to be larger than 10 milliseconds, the throughput degrades by 90%. So it should be 10 or 9. And now it decreases to less than 1 giga. And this happens gigabits per second. This happens even though we only have 0.0046% packet loss. So if we are transferring big scientific data, it might take days if this degradation happens. And ScienceDMZ tries to eliminate the loss or at least severely reduce it. So the ScienceDMZ is a network designed for big science data transfers on WAN, and it has 4 main components. The first component is the high throughput friction-free WAN path. So as you can see on the figure to the right here, the border router for an enterprise network is directly connected to the WAN. We will not introduce any security appliances or netting that might lead to packet losses. We should have direct access to the WAN with no application that might degrade the throughput. And the border router will be directly connected to the ScienceDMZ DTN data transfer node, which is the second component. So DTN, or again, data transfer node, is an optimized machine for high throughput or high data transfer. So on the other hand, if you see the red line, this one connects the DTN to the enterprise network. But because we typically have the enterprise network and the ScienceDMZ physically in the same location, the RTT will be very low. Having very low RTT means that packet losses will not have severe effect on the throughput, so we can introduce security appliances and netting. Now, as you can see here, we have some offline security appliances that applies on the green path or the friction-free path. And this is the security application tailored for high-speed networks. It's a passive, it's not interacting with the traffic, it's not adding any overhead. And the last component of ScienceDMZ is perfSONAR or end-to-end monitoring, which is typically performed using perfSONAR. So perfSONAR makes sure that the ScienceDMZ architecture is working as it's supposed to be. So we will always be verifying the throughput, the RTT, and so on. So we'll be discussing more about perfSONAR in the later slides. So the ScienceDMZ and perfSONAR are widely deployed across the US and the whole world. So as you can see here on this figure, many locations already deploy perfSONAR nodes and ScienceDMZ architecture, and also across the whole world. So now let's move forward and talk more about perfSONAR. So perfSONAR is a measurement tool for end-to-end path. So it's used by ScienceDMZ to validate that the WAN paths are working as they should be working. So a main concept behind ScienceDMZ is that the WAN should have no problems, and we should eliminate any or at least reduce the delays between the border router and the WAN. So to verify that the WAN is working well, after all, the WAN is a set of connected networks, we should have a mechanism to verify that's working, even though if we don't have access to other networks. So as we can see here in this figure, we have different networks, for example, Campus Network 2, Campus Network 1. These are different networks, and they have different administration in place. So you can get access to, if you belong to Campus Network 1, you can get access to Campus Network 2. But to verify that the path is working, you should have a monitoring capability. And this is what perfSONAR does. It provides you with a way to measure the throughput, not only the throughput, to monitor the performance, the overall performance, without having physical access to remote sites. So it helps troubleshooting performance issues like finding soft failures, and it's really important here to focus on this point, because if it's hard failure, it will be relatively easy to detect it. Because if we have hard failure, we can directly get the segment of the network that caused this issue. So we can just see where the error occurred, because it's no more transferring data. On the other hand, with soft failures, we still have data transfers in place, but the throughput is very low. So perfSONAR helps troubleshooting this type of issues. And as we said before, it's a key component of ScienceDMZ. Now let's talk about the architecture of perfSONAR itself. So perfSONAR in total has 7 different layers. So that's discovery, the tools, scheduling, archiving, configuration, and visualization. What's special about this architecture is that it supports plug-in architecture, especially the archiving layer. So it allows you to use a custom database that default settings use Logstash and OpenSearch, but you can use different storage systems. Another added value for perfSONAR is that it relies on open source tools, specifically in its tools layer. So for example, it uses iPerf for measuring the throughput, TWPing for RTT, and so on. So all these layers are connected through RESTful APIs. We'll discuss this more in details in future slides. And they provide coarse-grained measurements. This occurs because, as we said, it uses open source tools, which are software tools, compared to hardware elements. The granularity supported by perfSONAR is coarse-grained and not fine-grained. So what is the goal of our proposed application is to enhance the the performance of perfSONAR by introducing P4 switches. So by introducing P4 switches to the perfSONAR tool, we'll be able to get per-packet visibility, which is almost impossible using perfSONAR without P4. We need a hardware to have that computational power. We will be able to track per flow or flows individually. So we'll get all the statistics for the different flows in our network or that are being transferred. Another advantage of the system is that it's compatible with the current ScienceDMZ. So we're discussing this in details. As our system can seamlessly integrate with perfSONAR, there is no need to add anything at the level of perfSONAR as long as we configured the Logstash pipeline, which is this element, and with a simple configuration, we can seamlessly integrate perfSONAR with P4. And finally, our system, or the integration between P4 and perfSONAR, will produce high resolution measurements while minimizing the reporting rate. So here, when we say minimizing reporting rate, we are talking about adaptive sampling technique that depends on the variation of the traffic to manage the reporting rate. So this table here shows the comparison between perfSONAR and P4 perfSONAR. So for perfSONAR, the measurement type is mainly active measurements through the tests we are performing. For P4 perfSONAR, it's mainly passive measurements because we'll be monitoring a copy of the real traffic. Our system will have access to a copy of the real traffic. Having passive measurement collection will allow us to reduce or eliminate the overhead on the network. The measurement source for perfSONAR is the injected traffic, mainly the injected traffic. For the P4 perfSONAR, it's the real traffic because, again, we are monitoring the real traffic, and having access to real traffic or monitoring the real traffic produce more accurate measurements. The granularity of perfSONAR is limited to what the software tools it uses can provide. On the other hand, P4 perfSONAR uh, provides per flow and per packet granularity. It uses the P4 switch hardware, which gives much more computational power compared to the software tools used by perfSONAR alone. The visibility. So for perfSONAR, the visibility is mainly limited to the active test, to the duration of the active tests. For example, the throughput is performed once every 4 hours. So more or less, you'll be monitoring that specific metric once every 4 hours. On the other hand, for P4 perfSONAR system, you will have a real-time visibility over all data transfer. So as long as you have a data transfer, you should have visibility over the path that being held or the path that used to transfer the data. The reporting rate for perfSONAR, it's fixed in the sense that a human should manage it manually. On the other hand, before perfSONAR, it's adaptive. It depends on the measurements being collected by the P4 switch. There is no need for a human human intervention to modify it manually. And finally, endpoint failures. So perfSONAR points, measurement points, typically monitor the performance of the link or the path that connect two or more of them. So any device not residing on the path will not be monitored by perfSONAR. So and typically DTNs are not on the path between two different perfSONARs. This is one point. The other point is that perfSONAR does not have access to the traffic of the DTN itself. perfSONAR uses mainly, again, I should use mainly. perfSONAR mainly uses the active measurements. So it cannot detect when a failure is caused by an endpoint. On the other hand, before perfSONAR can detect that. So depending on the failure, it can classify it as if it was originating from the network, from the sender, or from the receiver. So we have been talking about before programmable data planes. Let's now describe more about it. So before programmable data planes, it will be referred to by later as PDP. It's a domain-specific processor for networking. The figure to the right shows a general architecture of the switch ASICs, the one that's implemented on the switch, the P4 switch, and how it processes packets. So this one is the data plane. Actually, this one is the data plane. So it has a parser component, and in this component, you can define custom protocols. So you can process custom headers depending on your application, the one you are implementing. And then you have the pipeline, match action pipeline. Different architecture exists, but in general, you have a set of match action tables. You implement the logic of your application in this in these devices or in these tables. And finally, you have the deep parser that connects back the headers you parsed with the payload of the packet. At runtime, you can use the control plane to push new rules to the data plane, so it's kind of interactive. So the added value of before programmable data planes is that it allows us to parse new protocols in the parser. It's fully customizable. It provides measurement events with high precision. And here it's in nanosecond resolution. So everything stored inside the data plane, we can access it from the control plane. This means that we can have access to nanosecond based events. For example, microburst, we might be able to detect them with nanosecond resolution. Finally, it runs custom application at line rate, which you mainly be implementing them inside the match action tables. This figure on the right, this one shows the comparison between typical CPU and the switch chip over the time. So, for example, in year 2000, the switch chip was 5 times faster than the CPU. Here we are talking about gigabit per second. In 2020, the gap increased to be 100 times faster than the CPU. So we are getting this added value, although we have a fully programmable device. Now let's move to the next component, which is the predictive model we used. So as we said before, there is no need for manually adjusting the reporting rate. The system will monitor the variation in the traffic, and based on the variation, it will adaptively report the measurements. And to implement this, we base our system on the linear prediction method. So the linear prediction method enables a system to predict the future value of a variable based on the observed values. So we should be observing the traffic for a specific time duration or a specific set of or specific number of observations. After observing the network, we'll try to build a linear model out of the measurements. If our linear model was able to predict future values with relatively high precision, we can say that we know the traffic pattern. This means that we can reduce the reporting rate. On the other hand, if we were not able to build a linear model out of the observed measurements, we should increase the reporting rate because there is variation in the observed measurements. And to calculate predict values, we use this formula. So in this formula, xpn plus 1, it's the predicted value for the next sample. Xn, which is here, is the most recent sample. N is the number of actual samples considered so far, and this one is a hyperparameter. XITI represent the value and arrival time of the ice sample, respectively, and delta T current is the time gap between the most recent sample and the next sample. So to adjust the sampling rate, what we have to do is to adjust delta T current, but actually the system will automatically adjust delta T current based on the variation of the traffic. And now let's go to the proposed system and have an overview of it. So if you consider this image, you can see that the WAN is directly connected to the core switch, and we are getting a copy of that traffic through optical taps to a programmable switch. So the implementation or the deployment is passive. It will not be affecting the real traffic, but it will get copy of all the packets. So the packets coming to the core switch and exiting from the core switch will be copied to the programmable switch. The programmable switch will be at runtime, at line rate, collecting the measurements on a per flow basis and storing them inside perfSONAR archiver. So as we said, the BDP will continuously generate fine-grained measurements at line rate, and it will selectively report to the archiver based on the adaptive sampling technique we employed. And we also introduce new measurements, Q occupancy and packet arrival time. So these new measurements are introduced to perfSONAR. perfSONAR does not support the Q occupancy, or at least a fine-grained Q occupancy. The programmable switch can monitor on a per packet basis the Q occupancy of the switch. So we'll not be reporting it on a per packet, but we are monitoring it on a per packet basis, and we are also having per flow packet inter-arrival time monitored. So how does the adaptive model work in action? This figure shows a high-level illustration of the process. So here we have two flows. Let's consider call them the blue flow and the red flow. The blue flow is relatively stable compared to the red one. So the data plane will be monitoring both flows separately, and then we'll be extracting the measurements. The control plane will be extracting the measurements of the both flows at the same rate. So we have the same extraction rate. And when we say extraction rate is the rate of which the control plane is retrieving measurements from the data plane. So for the two flows, we have the same extraction rate, but the control plane, based on the observed measurements, it will be adjusting the reporting rate. The reporting rate is the rate at which the control plane is sending reports to the archiver. So we are getting samples from the data plane, processing them to create reports, and then adaptively adjust the reporting rate of these reports based on the variation of the traffic. So here, one added value of the system compared to the linear prediction method is that the extraction rate is constant, the rate of which we are extracting from the data plane. And another advantage is that we can have the decision on a per observation base and not per sample base. So the difference between saying per observation and per sample is that the adaptive model is not only considering the samples or the reports it's sending for the archiver to predict the future values. It's considering all the observed data points extracted from the data plane. So this severely enhances or has a great influence on the accuracy of the model, as we'll be seeing in the results section. So the control plane is configured to extract measurements at a constant rate. By considering a constant extraction rate, the formula to calculate the predicted value will be simplified as follows. Now, after we calculate the predicted value, we should compare it to the actual value after we retrieve it. So assume that we predicted the value of element x n plus 1, and the predicted value is x p n plus 1. After we retrieve the element xn plus 1, we should see how accurate our model is, or how accurate that prediction was. And to calculate this, we divide the predicted value over the actual value, and the result should be bounded by 1 minus sigma and 1 plus sigma. So this is the range of allowed error. So if the error m is between 1 minus sigma and 1 plus sigma, knowing that sigma is a hyperparameter going between 0 and 1. So if m is within sigma from unity, then the model was able to, or the system was able to create a linear model of the traffic, and we can reduce the sampling rate. If the error is not bounded by sigma from unity, then we have to increase the sampling rate, or the rate of which the control plane is reporting measurements to the archiver. So this table shows how we are configuring delta t next. Delta t next is the time duration or time gap between the last report and the next report. So if we have accurate prediction, or if the error m is within sigma from unity, we'll set delta t next to be the minimum of delta t max and delta t current plus 1. So we either increase the current rate by 1, or the current sampling duration by 1, or Tmax, depending on the value we set for Tmax, because after all, we don't want to increase the duration too much, otherwise that will affect the accuracy. So we should have an upper bound on the time duration. And here it's really important to note that increasing the time between different between reports will decrease the reporting rate, because the reporting rate depends on the time. As the time increases, the reporting rate decreases. On the other hand, if the error is not within sigma from unity, we'll set delta T next to be delta T min, which is the minimum rate possible, and it's equivalent to the extraction rate. So every measurement extracted from the data plane will be reported from the control plane to the archiver. And delta T min, delta T max are the minimum and maximum allowed time gaps between consecutive reports, as we said. Now, how can we evaluate the system? The adaptive model we use the RME. The adaptive model aims to minimize the number of reports measured while sustaining low relative RME. So the RME measures the difference between a reported sample and the average of all samples with respect to the average of all samples. If you want to rephrase this one, what we are trying to do is to see how far is the average of what we reported compared to all what we observed, and then normalize it using what we observed. So this metric, or this the RME, this one is used typically to see if the value reported by an adaptive model are representative enough of the whole set of observations. So our goal is to keep this one small. The lower the RME, the better. At the same time, we should not increase the reporting rate too much. So the proposed system is capable of computing the following per flow statistics: the packet loss rate, the RTT, the throughput, the queue occupancy and the queuing delay, and the packet inter-arrival time. So all of these are calculated per flow except the queue occupancy. So the queue occupancy is it's measured on per router basis and not per flow basis. Besides these two measurements, we are calculating other measurements based on the aggregated values of all the flows. So the control plane will have access to all the measurement of different flows. Using this, we can calculate James Fairness Index. This James Fairness Index is used to see how fair is the allocation of the throughput on the flows, or the how fair is the available bandwidth is allocated on the active flows. And we can also calculate link utilization. How much are we utilizing from the bottleneck link or the link that's connected to the router? If it's not the bottleneck link, then it's only the link that's connected to the border router. So now the experimental setup, we have two different experimental setup. The first one is used to evaluate the adaptive model, and we'll have another one that's used to evaluate the per flow monitoring capabilities of the system. So to evaluate the adaptive model, we build this topology. It consists of two Juniper routers, the border router and ISP. They are Juniper MX204. We have a ScienceDMC, local ScienceDMC, connected through the two routers to a remote WAN emulated using NetM. And we have two optical tabs that copy the packet entering to and exiting from the border router and forwarding them to the P4 switch. And again, the P4 switch will be reporting the measurement to the perfSONAR archiver. So the first experiment we did was to evaluate the impact of sigma, or the error allowed to be done by the system, the adaptive model, sorry. So we are evaluating the impact of sigma with respect to the RME and the number of reported samples, because again, we should reduce the RME while also reducing the number of samples we reported, or number of observation we reported. The larger the value of sigma, the larger the tolerance to error, because M is bounded. It should be within sigma from unity, or M is between 1 minus sigma and 1 plus sigma. And the test is a 2-minute test performed between the DTNs and we use 6 different values of sigma. So the values of sigma we use, as you can see in this figure, are sigma equals 0.025, 0.05, 0.075, 0.1, 0.15, and 0.2, sorry. And for different sigma, we are calculating the number of samples and the RME. The RME is the red line here, and it's the x-axis on the right. The x-axis on the left is the throughput. The green line is the ground truth throughput. When we say ground truth throughput, it's the throughput without deploying the adaptive sampling. So we are getting one sample every second without adaptively reducing the sampling rate. And the blue dots refer to the samples being captured by the adaptive model. So if we consider the first graph, this one, well, number 1, you can see that the RME is almost 0 because the tolerance is very low. But at the same time, we had 96 samples out of 120. I'm saying 120 because it's a 2-minute test, and we have a total of 120 sample, 120 throughput measurement without sampling. So as we increase the tolerance to 0.05, the number of samples reduced to 72 out of 120, and the RME shows a slight increase. So the RME is still relatively low. The number of samples is around the half compared to the total number of throughput measurements. If we increase the tolerance more, we again reduce the number of samples, but we start to see relatively high values of RME, or the relative mean error. This is not something we should do. We should always keep the RME low, otherwise the adaptive model will not be reporting representative samples. And as we increase sigma above 0.075, like to 0.1, 0.15, and 0.2, the RME starts to have relatively large values. So from this graph, we noted that we did the same experiment multiple times, and we almost get the same results every single time. So we used the sigma of 0.05 as the best combination between the number of reported samples and the RME. Now we compared this adaptive system, the proposed adaptive system, with the LP method and another adaptive model, which is the multi-adaptive sampling technique, MAST. So MAST is another adaptive model that's based on the LP method, but the main difference is that it not only adjusts the number of the duration or the reporting rate, but it also adjusts the number of samples at each epoch of reporting. So the approach we propose, and LP only adjusts the reporting rate, and depending on delta T current, will be reporting the next measurement. However, MAST adds both the number of reports, adjusts the number of samples, and the duration, the delta T current. So for the 3 different systems, we set sigma to be 0.05, and the results of the experiment is shown here. So this experiment is again similar to the previous one. It's 2-minute test between the internal DTN, the external DTN. The ground truth is the green line, which is shown here. The proposed system is the blue dots. MAS is the yellow dots. Linear prediction method is the orange dots, and the RME is the red graph here. So the proposed system almost was able to capture the full pattern of the throughput value. As you can see here, the ground truth and the proposed system are aligned, almost fully aligned. We have some differences, but still the RME is relatively low. Now, if we go to MAST, it's performing better than LP, but worse than our proposed system. The RME increases in some occurrences, and for some chunks of the pattern, it's not fully captured by MAST. Now, if we go to LP, it had the worst performance. The RME increases to reach 0.25 in some for some chunks of the pattern. So here it increases, the RME increases to 0.25 because LP will increase the reporting rate. Sorry, it will reduce the reporting rate, and after that we'll have a change in the pattern. So it will not be able to directly capture this pattern, the new pattern, and this results in high RME. Another way to compare between the three systems is through using cumulative distribution function of the RME for the three systems. And it's plotted here in this graph. So on the y-axis, we have the CDF. On the x-axis, we have the RME. And as you can see, the proposed system had the best performance. So around 98% of the time, the RME was less than 0.04. And the maximum observed value is 0.06, so this is relatively low. On the other hand, MAS and LP have some values that reach 0.2 or above. MAS has slightly better performance to LP when it comes to the cumulative distribution function of the RME, but overall it performs better than LP. Now I'll show you a 1-minute demo of of the adaptive system with 3 different sigmas. So sigma. Okay. So I have iPerf test between 2 different perfSONAR nodes, perfSONAR 1 and perfSONAR 2. And here we have the ground truth throughput with, so this one is alpha, but it should be sigma. Sigma equals 0.05, sigma equals 0.1. And here we have the number of reports. So for the ground truth, we can see that the number of reports is 5. Here we are aggregating over duration of 5 seconds. So it's shown as 5 because every 5 seconds it's updating. The number of reports for sigma set to 0.05 is lower than the ground truth, while we still have almost the same pattern. Now, if we go to sigma set to 0.1, we can see that we can't capture all the pattern here, but the number of reports is very low. So you're depending on what your objective is, to reduce the number of samples or keep precise monitoring of the pattern and the real data. You can adjust the value of sigma. So now I will show how the throughput and the RTT measurement are really deployed in the system. So now the same as before, but now I'll be showing the RTT and the throughput, and I will also only have a sigma set to 0.05 and compared to the ground truth. So here we have perfSONAR 1 and perfSONAR 2, and we have a throughput test. The graph here shows the throughput. The green line is for the adaptive system. The yellow line is for the ground truth. Here we have the RTT, same number of samples. For throughput samples, number of RTT samples, and the lower 2 graphs are the throughput RME and RTT RME. So sure, if I can go a little bit here. As you can see, we almost captured the pattern when and the number of samples is relatively low for both the throughput and the RTT when the connection is kind of stable. The RTT is stable and the throughput is stable. Now what I will do is I will add some noise to the RTT to see how the system will automatically adjust the sampling rate to capture this variation. So as you can see, the throughput here, the RTT, we have variation. The number of sample increases. We have slight increase in the RTT, but as we increase the number of samples, we can keep the RTT minimal. It's around 0.02 or less. And all the new pattern is fully captured, as we see here. So next we'll be evaluating the capability of the system to monitor per flow statistics. So now instead of having one external DTN, we have 3 external DTNs, one internal DTN or ScienceMC. They again are connected through 2 Juniper routers, border router and the ISP. The P4 switch is deployed passively, and the bottleneck link is the link connected the border router to the ISP with capacity of 10 gigabits per second. The first test we did is to show how we can have real-time monitoring of the throughput, key occupancy, packet loss, and RTT. The scenario is as follows. We have two data transfers between DTN0 and DTN1 and DTN0 and DTN2. So DTN0, we are referring to the internal science DMZ, and each of the external DTNs have value DTN1, DTN2, and DTN3, and they belong to three different science DMZs, external science DMZs. So at time equal to 0, we had two data transfers, one between DTN0 and DTN1, and the other between DTN1 and DTN2. After that, at t equals 16, 8, 25, here, we introduced a third flow. The propagation delay of the three flows are 50, 75, and 100 millisecond for the three different connections, respectively. So as you can see at the start of the experiment, the two flows, the flow with DTN1 and flow with DTN2 almost occupied the full link, which is around 10 gig. The occupancy pattern is repeating itself, the RTT the same, and the packet loss is relatively low. Now here it's important to see how the RTT is increasing as the queue occupancy increases. So the queue is set to hold at most around 50 milliseconds of traffic. So as the queue is building up, the RTT will increases because of the queuing delay of the system, of the router. That's why it's really important to have large queues, especially to reduce packet losses, because every time the queue is full, we'll observe packet losses. As we see here, packet loss will severely degrade the throughput. And these decreases in the throughput here are occurred because, for example, because of this event here in the occupancy. And this is the added value of the system, because now we can understand why the throughput, for example, here is decreased by just observing the queue occupancy graph. So when we introduce the third flow, the flow between DTN0 and DTN3, the blue flow here, we can see that we have bursts of traffic in the queue. The burst of traffic was interpreted to an increase in the RTT and significant increase in the number of packet lost. So by monitoring all the graphs, we can see the influence or the effect of having a new flow, how it absorbed most of that of the bandwidth, how it affected the queue occupancy. The queue occupancy, on the other hand, affected the RTT and the packet loss percentage. And you know that this increase in the packet loss percentage is because the the router buffer was not able to absorb all the packet when the flow joined the network. So this allowed us to have a comprehensive overview of our network. Beside calculating such metrics, we can get the fairness and the link utilization. We can calculate them in the control plane. So the graph here shows the link utilization and the fairness of the same experiment we had in the slide before. You can see that the link utilization is almost 100% most of the time. The only time it's not 100% is when we have packet losses that are caused by the queue. For example, here, the link utilization is not 100% because we had a packet loss, as shown here. When we had a packet loss, that's caused by the queue occupancy. The throughput will decrease for all the flows. Throughput decreases means we are no more utilizing the link. The fairness is based on the Jane's fairness index. It's between 0 and 1. A totally fair system has an index of 1, and totally unfair system has an index of 0. So the closer to 1, the more fair the allocation of bandwidth to flows is. Now, as you can see here in the fairness, at this time, the fairness decreased. It was 1 unless at this specific time it reduced, and then start to go up to 1 again. And to understand what's happening here, we can just observe the throughput graph. because when the new flow arrives, it absorbed most of the bandwidth or consumed most of the bandwidth. So the allocation for the three flows is not fair. One flow, the blue flow, is consuming most of the bandwidth, but as time passes, the three flows start to converge and have fair allocation of bandwidth. This is based on the congestion control algorithm based, but that's the reason why the fairness start to increase gradually till it reach almost 1 here as the three flow converged. So these are some of the metrics supported by the system. We are not able to show everything because otherwise the presentation will be too long. But before concluding, I want to describe a new library that's still under construction. So the whole system I described, we are trying to build a new library that shows the user or the learner how everything is implemented. So the new library P4 is still under construction. We are currently working on it. The lab library illustrates the process of combining perfSONAR and P4, how to combine the measurement collected by the P4 switch to Logstash and OpenSearch or the archiving layer of the switch. The user will have access to the library through NetLab platform, and I will show you shortly how to get access to NetLab. And so far it has 8 labs. These are the labs that are in the lab library. Now let's have a quick video showing how to log into NetLab for anyone interested on having more details about the system we are having. So the first thing, we should have account, and you can email Jose Gomez to give you the credentials. After you log in for the first time, it will prompt you to change the password. You can put your new password and confirm it. After that, you have to have a new lab reservation. You choose the lab series. In this case, showing for IPv6, but for you it will be the P4 perfSONAR. You select the lab, the one you want to learn more about its topic. Make a reservation by clicking on the red line, specifying the time of the reservation, and you will have access to everything. So after you have reservation, you just have to enter to it. You'll have manuals there. You will have the virtual machines that shows you how to implement the system. So now I'll show another demo that briefly goes over one of the labs that we already prepared. The one that shows how we can connect the control plane or how we can connect the P4 switch to the archiving layer of perfSONAR and then visualize everything using Grafana. So everything happened here have detailed explanation in the manual lab. And this is the topology we are using in this specific lab: one perfSONAR archiver and 2 hosts connected through P4 switch. So P4 here is deployed inline, but in the proposed system, it's passive. It deployed passively just to make things clear. Now here I'm showing how inside the archiver we created our own pipeline. So inside the perfSONAR archiver, you create your own Logstash pipeline that will be processing the custom measurement you are sending to Logstash. And Logstash is the pipeline responsible for receiving the measurements and storing them inside OpenSearch, the database of, the database of perfSONAR. So we have 3 filters, or one filter, the input file and the output file. We are using the TCP input plugin because we are getting the data from remote machine, which is the P4 switch. And for the output plugin, we have OpenSearch, and we are using P4 index to store the data. So you should specify the index. In case of perfSONAR, you will be using pscheduler index. For P4, we'll be using P4 index. This one is fully customizable, and we discussed this in the lab. We started the P4 switch 1 month ago, and now we'll be having one iPerf test between H1 and H2. After having the test, we'll be going to a Grafana dashboard that's connected to OpenSearch database, and that allows us to visualize the throughput test. So as you can see here, as the test is, as we are sending data, we at runtime observing the throughput values in Grafana dashboard. And we can do the same for different metrics, for all the metrics that I already showed, discussed in the slides before. So for now, we only have throughput, but we can easily add the RTT and the other metrics. And here we are showing how the data source of this dashboard is from OpenSearch, and how we are using the P4 index, the same one we specified in the archiver configuration file. So this is what I wanted to show. Moving to the conclusion, in this presentation, we described an extension of perfSONAR using P4 switches. The P4 switch provide per packet visibility and line rate computation. The scheme augments perfSONAR by tracking flow individually, provide high resolution measurements and iterating over passive traffic. And finally, the system uses an adaptive mode that selectively reports the measurements to reduce the overhead on the perfSONAR archiver. So thank you for listening. Please let me know if you have any questions.
Yeah, thank you. That's very interesting stuff.
Thank you.
And anyone have any questions? I guess I had one. Where do you see, taking this from where you're at now into any sort of like even semi-production or area to test it out and run different stuff through it? More of an HPC center, more of something in the data center and cloud, where you see some applications for this?
So actually, we'll be deploying this inside the data center in USC, University of South Carolina. So the whole system will be deployed internally here. We are working on that. But yeah, we'll have a real deployment inside our data center for the full system.
Okay, great. Do you see yourself presenting that to this community at some point, whether back on one of these calls or even at an Internet 2 meeting or anything?
Uh, so we might do another presentation that shows the result of the deployment and sharing the details of the whole system. But not for now, we are still in the stage of implementing them in the data center. We did not fully implement everything there. But yeah, of course, we can have another presentation that shows what we did and our results.
Okay, great. We did have one question in chat from Cindy. How do we get credentials for that lab cluster again?
So Cindy, for now, the lab library is still under construction. We need like 1 or 2 months maximum to finalize everything and get everything ready. But in case you want access, you can always send email to me, and my email is here. I will talk to Jose and give you credentials to access the platform. I will give you the URL of the platform, username, and password. You are welcome.
Okay. Any other questions from anyone? I think it's Friday afternoon, so.
Everyone's tired.
Yeah. Okay. I'm sure, like I said, your contact info is in there. If anyone does have any questions, they can reach out. So, and I will get this recording published. I'll work with Jason on that to get this out there. And thanks everyone for coming along, and thanks again for a great presentation. And we'll see you next time. All right,
Thank
thank you.
you.
All right, have a nice day, weekend.
Very well. Thank you.